In order to describe electron orbits, we need to consider them as behaving like waves. These waves exist in orbitals. We cannot say with any degree of precision where the electron in an orbital will be. We can only consider the places where it is most likely to be. This diagram on the top left shows how we might plot this information. Imagine a picture of your house with transparent walls. Somebody tracks your position in the house and places a dot at the start of every minute to indicate your position in the house. There would likely be a large collection of dots in the living room and around the bed, showing that you spend a lot of time there, and fewer in the bathroom. This spread of dots works in the same way and shows that the electron spends most of its time in a sphere close to the nucleus. We often simplify this picture to a solid sphere, which shows an area in which there is a very high probability of finding an electron. In order to understand bonding, we need to be able to understand a property of waves called interference. When two identical waves meet at the same part of their wave, we say the waves have the same phase, the waves combine to make a larger one. This is known as constructive interference. When two waves are out of phase, that is to say one crest on one wave meets a trough on another, they cancel each other out. The animation on the right of the frame shows this happening. The slits start two new waves passing through. In some places, the waves constructively interfere with each other. You should be able to see lines along which the waves destructively interfere, leaving no wave in that position. Electrons can behave in this way too. We often use different colours or a plus or minus symbol to indicate the phase of an electron wave within an orbital. In this example, two hydrogen atoms meet with s orbitals that are in the same phase. This leads to constructive interference between the nuclei of the two atoms, and there is a build-up of electron density we call a covalent bond. We've gone from two spherical-shaped atoms to a sausage-shaped molecule as the orbitals combined. If you were to look exactly down the axis of the bond, so you were only able to see one atom, it would be difficult to know if you were looking at an individual s orbital or a molecule. We call this type of bond a sigma bond because it looks like an s orbital down that axis, and sigma is the Greek letter for s. If electrons go into a bonding orbital, this results in a bond being formed or strengthened. Just like when a crest and a trough meet and cancel out, when two orbitals of opposite phase meet, they result in no build-up of electron density between the nuclei. We call the result an antibonding orbital. A node is a place on a wave where it has zero amplitude. Notice what is known as the nodal plane in the antibonding orbital. There is a plane which has no electron density between the two atoms. No bond is formed. If electrons go into antibonding orbitals, this results in the bonds being broken or weakened. We can use this principle to explain why dihydrogen forms, but not dihelium. S orbitals can meet in two ways, as we've seen. One combination is energetically favourable and results in the formation of a bonding orbital. One combination is unfavourable and results in an antibonding orbital. Each hydrogen atom has one electron in its s orbital, and we put the electrons into molecular orbitals following the same rules as we do for putting them into atomic orbitals. The electrons go into the lowest energy orbitals first, spin aligned if there are multiple degenerate orbitals, that's to say of the same energy, before they get paired up. In this case we have two electrons in the sigma bonding orbital and none in the antibonding orbital, labelled sigma star. A single covalent bond has been formed. We call the highest energy orbital with electrons in it the HOMO. The next orbital up is known as the LUMO. Chemistry usually involves moving electrons into or out of these orbitals. If we work through the same process with dihelium, which has twice the number of electrons, we find that we have the same number of electrons in the antibonding orbital as in the bonding orbital. When helium atoms meet, there is no net bond formed, so we would predict that He2 does not exist. Obviously, organic chemistry revolves around carbon, so it would be useful to talk about the way in which it bonds. At GCSE, you would have explained the bonding in methane by saying that carbon has 4 electrons in its outer shell, and drawn a dot-cross diagram to explain the rest. At AS level though, you learnt that that was not the whole story. In reality, carbon has 2 electrons in its outer shell, both in p orbitals. The other 2 electrons in the n equals 2 shell are slightly lower in energy in the 2s orbital. Yet we see carbon forming 4 bonds, so all those 4 electrons must be being used. Bond making is an exothermic process. It's energetically favourable. If the carbon were to invest a little energy in order to get these 2s orbitals into play, it could reap the benefits of forming 4 bonds instead of 2. This is exactly what it does. Instead of having 3 p orbitals and an s orbital, it forms a blend of the 2 types called an sp3 hybrid, thus named because it came from an s orbital and 3 p orbitals. Note how some of the characteristics of both orbitals are retained. There's a nodal plane just like in p orbitals, but one lobe has got larger, closer to being an s orbital. These 4 sp3 hybrids are degenerate, of the same energy, and so are all available to bond. As usual, this concept of hybridisation is only a model to help us simplify the ways in which atomic orbitals form molecular orbitals. In reality, the molecular orbitals we're representing tend not to be isolated to one atom, so don't be surprised if you find that orbitals don't always look exactly like these nice, neat little diagrams. Notice as well the little figure of 8 or dumbbell diagrams often used to represent these orbitals. They don't accurately portray the distribution of electrons, but they are easy to draw. Let's take a look at a couple of classic examples. Methane is formed from 4 sp3 hybrids, combining with the 1s orbitals on hydrogen atoms. We're forming 4 sigma bonds here. When we look at ethene, there is only the possibility for each carbon to form 3 sigma bonds, as that is the number of atoms it's bonding to. It makes up a hybrid set, which is very similar to before, known as sp2 hybrids. As the name suggests, it used 2 p orbitals and the s orbital to make this hybrid. This means that there is one spare p orbital which is not currently being used and remains intact. The 2 p orbitals on the adjoining carbon atoms can also overlap to form what is known as a pi bond. Pi is the Greek letter for p. Can you work out why this type of bond is known as a pi bond? As was mentioned on the last slide, this hybridisation idea is a bit of a model. So the molecular orbital that reflects the sigma bond between the 2 carbon atoms doesn't only have electron density between the 2 carbon atoms, as might be suggested, but you can clearly see the sigma bond in place. Which diagrams show bonding molecular orbitals? When a bond breaks, also known as fission or dissociation, it can do so in one of 2 ways: homolytic fission or heterolytic fission. We can use curly arrows to represent the movement of the electrons. A simple example of where we can see this working is dihydrogen, and we can use the dot cross model here. The covalent bond consists of 2 electrons, one came from each atom. We use a curly arrow with a full head to show the movement of 2 electrons. Here both electrons from the bond will go onto the right hand atom, leaving it with a negative charge, although 2 electrons moved onto it. One of them already belonged to it though, so its charge is only 1-. This would be written as follows. Note that the arrow starts where the electrons have come from, the bond, and finishes where they end up, the right hand hydrogen atom. We use a curly arrow with a half or fishhook head to show the movement of 1 electron. Here both atoms retain the electron they were already contributing to the bond. Neither gains a charge. We call these species with unpaired electrons radicals. This would be written as follows. Note that the arrow starts where the electrons have come from, the bond, and finishes where they end up, the atoms. Click on the highlighted areas to see mistakes that can happen when using curly arrows. These arrows show two pairs of electrons, both converging on the same carbon atom. This isn't going to happen. The result of these arrows moving in this way would be a negative carbanion with 4 bonds. The electrons from the carbon-chlorine bonds are actually going to move onto the chlorine atom, forming a chloride ion. Some atoms have gone missing here. Always check you have the right number of atoms in your product. With more complicated molecules, it can help to sketch out the product in pencil in the same configuration as you drew the starting materials, before trying to tidy up the structure to look correct. The chlorine atom is a radical. We're only moving one electron at a time, so fishhook arrows are needed. The curly arrow ought to start from where the electrons are, in this case the carbon-hydrogen bond. Assuming the other arrows are correct, one electron from this bond ought to have been used in forming a bond to the chlorine radical. This has left one electron which needs to go somewhere. A fishhook arrow is needed, starting from the bond and ending on the carbon atom. Click on the diagram to identify where the mistake is, then click Submit to carry on. In a homonuclear covalent bond, i.e. both atoms are the same, the pair of electrons are shared evenly. However, if one atom is more electronegative, it will be able to pull the bonding pair of electrons towards itself, resulting in more charge at that end of the molecule. The bond is said to be polar. The Greek letter lowercase delta is used to indicate a small change. In this case, where the small change is in charge density, we use it to represent a partial charge. Chlorine is significantly more electronegative than hydrogen, so whilst dichlorine is non-polar, HCl is polar. Nucleophiles are species that have a lone pair of electrons available to form a covalent bond with electrophiles. They'll be found with either a full or a partial negative charge on one atom. In this example, ammonia is attacking chloromethane. Ammonia can act as a nucleophile because it has a delta negative nitrogen atom and a lone pair of electrons. One curly arrow shows the formation of a bond to the carbon atom, which itself is delta positive due to the electronegativity of the neighbouring chlorine atom. This bond will be further polarized by the approaching ammonia, so the polarity is not that relevant, as I'll mention later. As the new bond is formed, the carbon-chlorine bond will break at the same time. The chlorine atom is substituted out, so the process is known as nucleophilic substitution. The chlorine atom here is acting as a leaving group, and although this may not have been mentioned at A-level, how good your leaving group is really what infers nucleophilicity on our electrophile, not the partial positive charge. You'll have seen at A-level that bromine can attack an alkene without being polar, because it is readily polarized as a consequence of the way in which the two molecules meet. This kind of behavior goes beyond neutral species though. Although it seems counterintuitive, you can in fact have electrophiles with a negative charge, as long as they have an effective leaving group. A glance at the molecular orbitals shows the HOMO of the ammonia as the lone pair, and that it can overlap with the LUMO on the chloromethane. Observe the lobe behind the carbon atom ready to form a bond. Note that this orbital is antibonding with respect to the carbon-chlorine bond, which explains why that bond breaks when electrons go in here. Because the ammonia can only attack from this side, there is a reversal in the stereochemistry around the carbon, like an umbrella being turned inside out. This is known as a Walden inversion. Nucleophilic substitution can follow two main pathways, which involve everything happening in one step or over two separate steps. We call these pathways mechanisms. In the example we just saw, the whole process occurred together. If we were to measure the rate of the reaction whilst changing the concentrations of each of the reactants, we would find that they both affect the speed at which the reaction takes place. This tells us that they are both involved in the slowest or rate-determining step. And as there are only two reactants, there must only be one step. The reaction proceeds via a transition state where there is a bond being formed and broken at the same time. This transition state is not a stable molecule you could store in a jar, although we do have techniques for trapping and identifying high-energy intermediate species in reactions. Imagine the reaction profile as a hill and the chemicals as a ball. On the plateau to the left, our reactants will sit quite happily. If we input some energy, we can push our imaginary ball to the top of the hill, but once there, it will always slide off one side or the other. As two molecules are involved in the rate-determining step, we call this bimolecular nucleophilic substitution, or SN2 for short. Another pathway a nucleophilic substitution can follow involves two different steps. The rate equation shows that only the haloalkane is involved in the rate-determining step, so something must happen to that molecule which has a large activation energy and is therefore slow before a second, faster step with a lower activation energy can proceed. In this case, the slow step with a large activation energy involves the breaking of the carbon-bromine bond and happens independently of the hydroxide ion. This leads to the formation of a reactive carbocation which the hydroxide ion can attack to form the product. Notice that the chemical in this example forms a tertiary carbocation, i.e., there are three other carbons surrounding the carbon with the positive charge. Whereas if this mechanism had occurred in the last example, there would have been a primary carbocation, as there was only one adjoining carbon atom. This is no accident and will be explained on the next slide. The carbocation is planar and has a p orbital with no electrons in it. Notice also that there is a reactive intermediate here, so our imaginary ball can settle for a short period in this hump, but it only takes the slightest nudge to push it down to the products. As you might guess, because only one molecule is involved in the rate-determining step, we call this mechanism SN1. We can explain why primary haloalkanes tend to undergo SN2 and tertiary haloalkanes SN1 by comparing the stability of the respective carbocations and the ease with which a nucleophile can attack the haloalkane. As long as pop-ups aren't blocked, you should see a new window appear around now which will give you a three-dimensional look at our tertiary haloalkane. Consider first where the nucleophile needs to attack. The lobe of the molecular orbital indicated in the main slide is where the nucleophile needs to get to, but it's protected by the surrounding hydrogen atoms on the methyl groups. We say it is sterically hindered. There's no way the HOMO of a nucleophile will achieve effective overlap with this lobe of this orbital. You can now close the pop-up window. Once the carbocation has been formed, it can be stabilized in one of two ways. Although there is not a significant difference in electronegativity between carbon and hydrogen, there is a slight difference. Methyl groups, as a result, can weakly push charge towards adjoining atoms. We call this an inductive effect. Also, adjoining sigma bonds, highlighted here in red, can stabilize the vacant p orbital by forming an extended molecular orbital. This is known as hyperconjugation. You could imagine hyperconjugation as being like two resonance forms which both tell us a little bit about the whole picture of what's going on. To some extent, the carbon-hydrogen bonding electrons can move towards the positive charge to stabilize it, and this latter picture is an extreme form of that situation. In reality, what we see is a blend of the two resonance forms that will have more in common with the left-hand picture overall. There are two things to consider that will affect the speed of nucleophilic substitution. One is the attractiveness of the delta-positive carbon to the nucleophile, and one is how easily the carbon-halogen bond is broken. As we move towards the top of the halogens, the strength of the bond will increase as the strength will be shorter. This would suggest that the higher halogens would form less reactive haloalkanes. However, they will also create a more polar bond, having the reverse effect. One way of seeing which effect wins out is by adding some silver nitrate solution to the reacting mixture. As the halogen is substituted out as a halide ion, it will form a silver halide precipitate. Experiments show that silver iodide precipitates form first, suggesting that the strength of the bond to be broken is more important than its polarity. This echoes what I suggested in an earlier slide. The existence of the partial positive charge is a bit of a red herring. It's the existence of an effective leaving group which infers electrophilicity on our nucleophile. In fact, this point can be stressed even further if you look back at the electronegativity chart I included earlier. Take a close look at carbon and iodine. Although iodomethane is the fastest of the haloalkanes to react, carbon and iodine have identical electronegativities, so the bond isn't even polar. The opposite of a nucleophile is an electrophile. These are species that can accept a pair of electrons from a nucleophile to form a covalent bond. The classic example of an electrophilic reaction is the addition to alkenes. Here a pair of electrons from the pi bond can attack the hydrogen in hydrogen bromide. Bromine can accept a pair of electrons from the bond to form a bromide ion. Notice the similarities of the first step to SN2. We have a source of electrons which move towards a species which happens to have a partial positive charge, but more importantly, it has a leaving group that can be displaced. In the next step, we have a carbocation. The carbocation could have formed on the end or the middle carbon of the molecule, but as we've seen, primary carbocations are less stable, so by far the major product is 2-bromopropane. Reactions that proceed in this way are called Markovnikov additions. If chemists want to add to the other carbon of the alkene, they have to use another method. That concludes this activity on organic mechanism. The links at the bottom are worth taking a look at. The last link includes lots of examples of reactions you will not yet have met, but it's a good tool for practicing using curly arrows.